Well, good evening, everybody, and nice to see many of you again. Um, this talk is really just the outgrowth of a whole lot of time operating without commercial power under various, whether it's a field day or a an actual outage or a experimental something you're doing up in the mountains, whatever it may be. Um, so we try and coalesce some of the information, and some of you, I'm sure that there's a lot of this you already know, and if some of you are engineers and I say anything that you disagree with, please chime up. um, so the first thing, you have to take a look at the equipment you're trying to power, and that means, what is it you're trying to do? You call that define the mission. Are you going to be out there for at a parade for a day? Are you going to be several days out for a 100 miler, or are you going to be out for weeks at a time? Are you operating just daytime, just nighttime, or around the clock? And what's your role? If you're a net control at an incident command post, I mean, you may have a lot more power requirements in terms of time than somebody who's out at a checkpoint or something and reports in, a couple of times an hour or less. What bands and modes are you going to need? And that kind of defines how much gear you're going to take. And then you have to start looking at what that equipment requires. And we'll talk about that in a moment. You also have to be concerned about, um, you know, how you're transporting this stuff. If you have to climb up a hill or climb up stairs with equipment, you're not going to go for a linear power supply that weighs 50 pounds. You're going to go for something light. So also, if you're going to be fixed in one place, that sets certain opportunities for you. If you're going to be moving around, that may provide some limitations. Indoors or outdoors, you're going to be remote by yourself, or you're going to have a bunch of people around. All these things can affect how you use your equipment, what equipment you bring, and therefore what power you need. Now, you could say, look, I have 1,000 amp hours worth of batteries. If I have that, I'm never going to run out of power. Well, that may be true, but can you transport that? And is that going to be compatible with the kind of operation you're going to have to do? So the idea is you don't need, you don't want to bring a lot more than you need in terms of power capacity, but you don't want to find yourself short either. And obviously, the estimated time that you're going to have to operate can vary, especially if somebody else told you, oh, you'll only be there for 2 days. Well, that may change. So you'll want some safety cushion, and we'll talk about that. You're going to power your stuff AC or DC. Obviously, AC has, assuming you have a generator or something, it's a lot easier to distribute over long distances, and it'll support higher power levels. But it may be, if there's only, say, one master generator there, it may be less reliable. It may be in greater demand because more people other than just you and your station need to use it. And of course, it's always dependent on the availability of fuel, subject to the solar generators, which we'll talk about near the end. DC, of course, is a lot more flexible. As we know, there are tons of sources of 12-volt DC, from emergency lighting in a building to car batteries to solar, solar panels. And most of our gear is designed for 12-volt DC power. So we're going to really be focusing, for the most part, on DC power, and we'll talk a little bit about AC at the end. Of course, you may have certain equipment that requires AC, so you can use a good inverter, and you want one that doesn't generate a lot of RF noise or is very inefficient or makes your equipment act weird. And that means generally you want a true sine wave inverter. And they're much easier on sensitive equipment, including your computers and so on. Of course, it's not hard to make DC from AC. That's what we normally use at home. If we got a home station, we've got a linear supply, which is the ones with their transformer and filter capacitors and so on. Now they typically run about 60% efficient, but if you're in a situation where there are transients, like on a mountaintop, they can absorb the input transients a lot better than a switching supply. Switching supplies are a lot lighter weight. I mean, by a factor of 3 or 4. They are much more efficient in terms of how much how much power they suck in order to produce whatever you need. But if you're in a high RF site or where you may have a lot of lightning nearby, they are probably not the best choice or you better have a spare because they can be much more susceptible to that sort of thing. Uh, if you have AC with a battery backup, the one thing you don't want to do is just take your 12-volt supply output, parallel it to the battery, and then hook it to your equipment. Because if something fails in the power supply, and some of those power supplies have what's called a crowbar circuit, which would basically provide a dead short across the battery. That's not a good thing. So there are various devices that use mainly use diodes, low loss diodes, to isolate the two sources of 12 volts, the AC based and the battery based. And these are a couple of examples. Unfortunately, I think the KI0BK ones aren't made anymore. I grabbed a couple. They're good for about 25 amps, which is fine if you're going to run a mobile rig and a computer, stuff like that. Now, selecting your equipment, you need to take a look at how much power that equipment requires, and there can be a lot of variation in that. And by choosing the right equipment, you can find that your operating time on a given amount of power can be extended considerably. Oops, let me jump back here a minute. I remember, I think it was the old IC706 little portable HF radio. One of the early ones were fairly compact. I think their receive draw was something like 2 amps, and whereas some of the other, like my K2 or K3, were drawing in the hundreds of milliamps, so orders of magnitude lower when you're receiving, which often most people are doing a large percentage of their total operating time. Also, watch out for the range of what voltages your equipment can use. Um, if you look at a lot of the modern mobile radios, for example, VHF, UHF. Let's say you're out there doing comms for a race or something, and everybody's on a 2-meter or 440 repeater. Uh, um, the radios want to see generally 13.8 volts, and there's a range over which they will operate. And when it gets below a certain point, they won't operate. So, if you've got a grid connected power supply, or you're running with your engine going in the car, you got 13.8 volts, pretty close. But if you've got a lead acid battery that is under load, you're not going to get 13.8. And as that battery discharges, you're going to get less and less. We'll talk about batteries in a little bit. Um, a standard 6-cell lead acid battery, whether it's deep cycle or, heaven forbid, you're using a starting battery, which isn't going to last very long. When it's full, yeah, you're going to get around 12.8, but when it's empty, you're going to get about 10.5, and it's sitting there decreasing all the time. Most of your equipment will not operate at 10.5 or 11 or 11.5, maybe even not at 12. So you got to think about the effective supply that you have, not just the nominal, what's on the label that says so many amp hours. Oops. Sharing stopped. Hang on. Let's fix that. Oop. Sec. There we go. All right. Are we back to no? Hang on. Let's get it right.
I saw the chart.
We want that one. There we go.
Here we go.
Okay. So let's take a look at typical lead acid discharge curve. That red line represents 12.5 volts, which we'll just assume for a moment is kind of the low threshold of where your equipment wants to be to operate normally. Well, you can see it starts up maybe close to 13 volts, and it's dropping and it's dropping and it's dropping, and a whole bunch of that capacity, that nominal capacity, is below that 12.5 volt threshold. So, you may get 100 amp hours out of that, but only a quarter of it may be useful. So this is why, and fortunately, we have an answer to that because we've had great improvement in battery technology. So you take a lithium iron phosphate battery, for example. Okay, there's that same threshold, but you've got like 80 to 90% of your discharge is above that line. It holds almost constant voltage and it just drops off right near the end. So the usable capacity of a lithium iron phosphate battery is a very high percentage of its nominal capacity. And that's not true for a lead acid. I mean, even whether it's a gel cell or an AGM, they're good for a while. And if you have loads that don't care too much, like 12 volt based fans or lamps or something, then you're probably fine. But that's a big issue if you've got to be operating for a long time with equipment that doesn't like being fed a very low voltage. You should also know your gear's current consumption. And this is because we're going to be doing some budgeting on this thing. How much power does it draw and receive? How much does it draw and transmit with low power? How much does it draw and transmit with high power? You can obviously look at the manual. You'll usually find that there. If not, set up a little test lab and take some measurements, see how much it draws, and make notes on that. If there are any settings that you can use to reduce the power drain, such as turning off a preamp when you don't need it, or a processor, turning the panel lights down or even off. All those things may have an impact on what the steady state drain is when you're operating. Let's look at now we talked about using low power. Well, obviously, my radio has 3 or 4 power settings, but I don't necessarily need all the power, so I'll just go low, and that'll help. If I go 10 watts instead of 50 watts, I'll use only 1/5 of the power. Well, that's not really true because the circuits are designed to operate at the maximum power, and the drop in input power is not proportional to the drop in output power. So here's an example: FT7900 Yaesu, really nice little dual band mobile radio. Okay, on standby or receive, it's drawing about 1/3 of an amp, which is great. If you're transmitting at 5 watts, here's a full power, 9 amps. Okay, at 45 watts. Oh, you cut it more than half, down to 20 watts. You're not going to cut the current drain down. It's only going to go down to 6 amps. Okay, well, I'll cut it in half again. It's only go down to 4. Okay, so you can see it's almost it goes down as the the square root of the power difference. 10 watts to 5 watts only gets you from down by about an amp. So something that's designed to operate around 20, 40, or 50 watts, if you drop that by a factor of 10, you may be dropping your current drain only by a factor of 3. This is why it's good to know the characteristics of your equipment. And again, if it's not in the manual, put a meter, a suitably sized current meter in line with your power source, transmit it with dummy load, and take some measurements. And another low power option would be, for example, let's say we're still in that VHF or UHF repeater situation, using a handheld where it's even when it's draining like a 1/10 of an amp when it's receiving. So maybe what you could do, let's say if you're in one of those situations like out in the field where you have to monitor a frequency, but you're not transmitting very often, you may just have a handheld, and if the handheld isn't enough to hit the distant repeater, You just put a switch in the antenna thing, okay, in the antenna line, and you can put the handheld on most of the time. And when you hear yourself being called, you need to transmit, switch over to the other radio. When you're done with that exchange, switch back to the handheld to monitor. And by the way, always make sure you have some sort of alkaline based or external uh, batteries available, or whether it's built in with a carrier, or whether it's an external with a plug. Make sure you can run the HTs off something other than their internal rechargeable batteries, because you may not be in a position to recharge them while you're out in the field. So we talked about developing a power budget. And what are we really talking about here? We want to balance out the loads, that is all the radios and lights and computer supplies and whatever else you've got. The sources, which could be battery, it could be generators, could be solar panels, could be an AC supply for part of the time, and the storage, which is the batteries. So for a given operation duration and the duty cycle, all these things will come into play as you're doing a budget. Is it going to be perfect? Absolutely not. But it will allow you to make educated guesses rather than uneducated guesses, and it'll get you closer to the right answer, whatever that happens to be. And of course, there's some math involved. So, being an old retired accountant, I just throw it on a spreadsheet. You can do the same, I'm sure. In fact, I'll show you the spreadsheet that I have later on. You'll be able to download it if you want to and play with it. So first, look at your actual operation. You've already looked at how much drain there's going to be on each piece of equipment under various conditions. So think about, how much of the time will this equipment be off? Am I operating daytime only and off for 12 hours? You don't know. If you're going to, how much time are you going to be in receive or standby? How much time are you going to be transmitting low? How much time are you going to have to transmit high? So whatever the variations and parameters are for your radio, think about what portion of a 24-hour day are you going to be in each of those modes. And then, of course, what's your transmit duty cycle? If it's an FM radio, you're on a FM repeater. Every time you hold the mic down, it's 100%, whether you're talking or not. On CW, rough average 50%. On sideband, rough average of 33%. So if you're doing a lot of HF work, you'll probably have a lower duty cycle. And then don't forget all those little accessories, lamps and modems and all that sort of thing that you may need. So here's the loads portion of a typical analysis. So in this case, I'm using a Elecraft K2 here. Okay, and I've already figured out how much it draws on receive, how much on low, how much on high. So those are the amps. Okay, and then I've also estimated how much time I'm going to be spending in each of those modes. I say, well, it's 24 hours around the clock, so I won't be having it off at all, but I will be listening about 80% of the time, transmitting about 20% of the time, split between high and low power. And you convert that percentage of a day into hours in each mode. And then you multiply that by the duty cycle. Obviously, when you're receiving, it draws all 25. When you're transmitting, it's on sideband, let's say, you're drawing about a third of the maximum current drain. So you can take those hours and you can take that time and you can convert that into amp hours per day. Okay. So now this gives you, for this radio, approximately how many amp hours it. Now remember, amp hours is basically, if you take an analogy to water, okay, water is basically it flows. You have to refill the tank. How big is the tank? How much do you have coming in the hose, and how much do you have to outflow? Same kind of idea. So amp hours is basically how much your outflow is. Now I'll take an old FM receiver, okay, and we take a look at those current draws under the various conditions, what percentage of time we'll think will be in each one, convert that to hours, throw in your duty cycle, and of course FM is 100%, and there again, it converts you to amp hours. So let's just assume we have these two pieces of equipment. We add these up and it says, okay, your loads are going to basically add up to around 51 amp hours a day. Okay, so now, when you do that with each piece of equipment, now you have a pretty good idea what you're going to, how much water is coming out of the hose, how much you're going to have to be able to provide in a day. Okay, now what are your sources? Are you have no sources at all? You're just going to start your battery, and when it's out, when it's done, you're done. That may be. And but let's say you do have some sources. Um, let's say you've got a you got a nice solar panel that puts out about 5 amps at peak current, and then you've got in the morning and evening hours it still puts out a couple of amps. So you can say, okay, well, here's I'm going to have 5 hours or about 20% of a day um, is going to be um, in peak output, and I'll be getting all 5 amps. So that works out to about 24 amp hours that it'll provide me. And even outside the peak hours, I'll still get another 14. And of course, at night I won't get anything. So there's 38 amp hours right there. Okay. Now let's say they're going to run a generator 15 minutes a day just to kind of keep medications cold or food cold or whatever it may be. If the generator is running all the time and you could draw the charger, then you got a whole different situation. But if let's say you only got 15 minutes a day, you're going to use your 40 amp charger. So 40 amps for a quarter of an hour, that gives you almost 10 amp hours. So you put the two together, that's going to be about 48 amp hours a day that you're going to have available. That's input. Okay, that's the hose filling the tank. Now you can remember what we had before. Our load was 51. Our available input is 48. There's obviously a shortage. So what that means is there's a limit as to how long you can run. If the sources are bigger than the charge, you know, the usage, you don't have to worry about it. But if they're not, you're going to have some storage to make up the difference. Okay, so whatever battery system we have, we're draining 3.2 amp hours a day. Okay, so now let's take a look at our battery capacity. Now let's say I've got my old Group 31 gel. Okay, it's a 96 amp hours. Um, target depth of discharge, what's that? Well, that is basically how much of that battery do you want to pull down? Now, remember I said in the case of a lead acid battery, part of that capacity you're not going to be able to use. But also with a typical lead acid, you don't want to drain it all the way down because that shortens the life of the battery considerably. Now, in a lithium iron phosphate situation, that's very different. You don't have to worry about that because you can charge it down to wherever the internal battery management system shuts off, and it's ready once you charge it up again, and you're going to get thousands of charges out of the thing. So that is pretty much a non-issue unless you want to use this as a safety factor for saying, well, they told me I was going to be out for 3 days, but it turns out it was 5 days. Okay, so there's a bit of a safety factor in here too that you can use, even if you're using a lithium iron phosphate battery, just from the standpoint of how much time can I drag this on where I'm using a net 3 amp hours a day. Okay, so in this situation, I say, well, I want to use plan on using about a third of the battery capacity. So that'd be 32 amp hours of drain. And if I'm going to be draining 3.2 amp hours a day, I could do this for 10 days, and then I'm probably going to be out of power. Uh, also, remember on battery capacity, I have a little asterisk here. Um, these Most of these batteries, especially the deep cycle batteries, are their amp hour rating is usually at a 20-hour rate. You should look at the specifications for whatever battery you're going to buy, but it says, if you're planning to draw it over a period of 20 hours, this is how many amp hours you get. But it's not linear. Again, if you have 20 say 100 amp hour battery and you're going to draw 100 amps in 1 hour, well, you're not going to get 100 amps in 1 hour. But if you're going to draw 1 amp for 100 hours, you'll get more than the rated capacity. So the shorter the period over which you're draining the battery, the lower the effective amp hours that you have available. Conversely, the slower you take this beyond the 20 hours, the more nominal capacity you'll have. And clear so far? Okay. Now, you've heard the old engineering joke, better, faster, cheaper, choose any two. Well, in battery capacity, it's usually been high capacity, inexpensive, or lightweight. Choose any two. However, things have gotten a lot better than they used to be in this regard. If you have lead acid, you got solid plate construction in a deep cycle battery. You've got big, lacy plates in a starting battery, because on this one, the idea is basically to put as much current into the load as you can for a short period of time and then recharge it right away. Whereas in deep cycle, that discharge is going to go on for a long time. You could, if you use a starting battery as a deep cycle battery, you'll do that about 2 or 3 times, and then you're going to have to replace it. And ask me how I know. The RV marine battery is kind of a hybrid. There's no real spec to it. Somebody told me once, well, the definition of an RV marine battery is anyone with a rope on it for a handle, but I don't think that's necessarily true. Now, with the lead acid batteries, you have choices in how electrolytes are worked. You have the flooded, which is typically your starting battery. It's a sloshy electrolyte. There are all sorts of handling issues surrounding that. You have the AGM, or absorbed glass mat, and the gel cells. Gelled and absorbed glass mat electrolytes are generally a lot safer to handle, to transport. And if you're not going to go with the lithium iron phosphate, these are the ones you really want to look at. And then, of course, you have alkaline NiCads and those things that are typically low capacity, lightweight for handhelds and so on. So your trade-offs are weight, cost, safety, and capacity. Flooded is cheapest, but as we said, poor choice generally. It's got a high self-discharge rate. There's spill hazard. When you're charging it, you have outgassing of hydrogen. I see people with, a car battery in one of these fancy, plastic cases. And I think, oh, that's great. So all the hydrogen is collecting in one place when you charge it. Not a good idea. In fact, I wouldn't have them in the house. You keep them out in the open and run some cables in. AGM and gel are both VRLA, which is valve regulated lead acid. They're higher cost than the flooded batteries, but they're generally spill proof if you follow the right charging regimen. There's no outgassing. They have pretty low, the good ones have a low self-discharge rate, which means if you have to sit it on the shelf for a month, it's still got almost all its capacity when you have to grab it and go. The AGMs tend to have a little wider range of acceptable charging voltages than the gels. They have the gels tend to have a higher number of charging cycles lifetime than the AGM, but they're not that far apart. So those are good. The lithium iron phosphate, although it has a higher initial cost, it's got more usable power. Remember those discharge curves, and they do require a specific charging protocol, typically constant current followed by constant voltage. And I usually just say, I'll take the charger that the manufacturer recommends or that they sell to go with it and use that. Typical trade-offs, my 96 amp hour gel cell weighs 70 pounds. It's a group 31. I picked that because it was the biggest one I could pick up with one hand and put in the car without hurting myself. And it cost about $300, and you'll get several hundred full discharge cycles out of it. The lithium iron phosphate 100 amp hour one that I have, it's about the same capacity, weighs only 26 pounds. Big difference. And the older I get, the more I appreciate that difference. Now, this used to say $800 because that was about the price, but the price of good lithium iron phosphate batteries is coming down. You'll still see some at 800, Battleborn, even Bioetto, and so on, unless you get your ham discount. But there are some other makers that have brought the price way down. And you'll get 1,000 or more full discharge cycles out of the thing, which means they'll probably outlast me. There's a fellow on the internet named Will Prowse, Prowse, and his thing is basically testing these batteries and helping people design off-grid or grid supplement systems for their homes and their businesses. He's very thorough about disassembling these batteries and looking at the quality of the internal connections, the structural stuff, the battery management system. I would recommend, if you want to look at some batteries you may not have heard of, check through his YouTube postings and see if he ever took a look at one of these things. Some of them he says are junk, some of them are really built beautifully. And so that may narrow your choices down and make your choice a little better. And as I say, the slide used to be 800 was pretty standard, and the prices have dropped so much. There's no reason not to get a good lithium iron phosphate battery anymore, especially considering the weight and the discharge capacity and the operating time that you get out of it. Let's say you have several batteries you're going to put in parallel so that you get more time out of them. The first thought is, well, I'll put all the positives together and all the negatives together. This could be as big a chain as you need. But the problem is all those cables have a little bit of loss. Okay. And if your load's here, it's going to draw more from the first battery than it will from the second or the third or the fourth. Okay. There are several better ways to do that. This is one of them. Okay. You're going to parallel the two pluses and the two minuses like normal, but you're going to draw the plus from one battery and the minus from the other. That basically means the charge and discharge path for each battery is the same total length, which means it's going to draw more equally between the two. And when you recharge them, it's going to recharge them more equally. When you have even more batteries, there are a number of there's a star configuration and so on. You can find some of that on the internet, but just this will give you the idea that, for long-term use, especially let's say you're going to charge and discharge every day with the solar system, over time, one battery is going to wear out faster than the other because it's getting more discharge than the first one. So that's something to consider. Now, when you're using batteries, if you got flooded types, it's a good idea to have protective eyewear when you're doing anything with them, whether you're charging or hooking them up or anything else, just because battery acid and eyeballs don't go very well together. For any kind of battery, try to avoid the disco chains, the long metal tools, anything that could hook up between those two terminals of the battery. If it's flooded, you want to make sure you avoid electrolyte spills. That means don't stick it in the back of your truck going up a bumpy mountain road and hope that it stays upright. Because I've known people who have actually had their nice Rhino liner partially dissolved because they let one of these batteries overturn and spill out battery acid. Again, for the flooded, make sure you ventilate well if you're charging, and never have them inside your operating position. Keep them out in the open air. The valve regulated and the lithium iron phosphates, of course, are safe for indoors and transport. Now, I approached the league some years ago about the possibility of lobbying the commercial airlines about allowing these batteries to be transported, the big, larger capacity batteries, say when amateurs are going down to an impacted area, hurricane area or something, they want to take enough power with them to be able to operate. And of course, you can't normally transmit those big batteries, transport them on commercial aircraft. They usually limit you. And I know in the case of lithium anything, they limit you to up to 2 batteries of 100 watt hours apiece, which is about roughly 8 amp hours. And that's obviously not going to be enough to sustain a long-term operation. I did when we went up to Alaska with my brother and his brothers and their friends. We were up at a fishing cabin up in Prince William Sound with no power. And the guys wanted to take pictures with their phones and stuff. So I brought 2 8 amp hour lithium iron phosphate batteries, which were allowable by hand carry, and a couple of DC converters so that I could charge a couple of phones at a time. And I was able to keep 10 guys' phones charged for a week using that system. That worked out quite well. And of course, whatever battery you're using, observe the proper charging regimen. As I said, it's different for lithium iron phosphate than for some of the VRLAs. the recommended charging voltage on a gel may be different from an AGM. It's a good idea to fuse at the, put a system fuse, if you will, at the battery end. And you say, well, all my equipment has either a fuse inside or in the power cord. Well, the problem is some of those fuses, especially the ones inside the units, they're designed to protect the unit, not to protect the system. Okay. And so you want fuses close to the source as you can, so that anything that happens, somebody drops their camping axe across your big power bus, you're not going to blow up the battery. And by the way, especially with lead acid batteries, they don't have any sort of current limitation on them. The current limitation is until when they blow up. Um, uh, a good friend of mine, now passed away, told me that in his studies, a lead acid deep cycle battery can produce in a short circuit up between 50 and 100 times their nominal rating, their nominal amp hour rating. So if it's a 100 amp hour battery, you could be looking at up to 10,000 instantaneous amps. Okay. And that basically will be an explosion. Fortunately, as we said, the lithium iron phosphate batteries have built-in battery management systems, and if they detect too much current going, they'll shut down. But fuses are a good idea. And if you've got big batteries or a bank of batteries, you want to use what's called a Class T fuse. Let me show you what that looks like. Okay, there's your typical automotive battery down here. This is a Class T fuse in a proper holder. These fuses have a couple of different ratings. They have their normal, if you exceed X current for too long, it'll blow and shut the circuit off. But then they have a second rating called the amp interrupt capacity rating. That is, how many amps, if you get a short circuit, how many amps, up to how many amps can we prevent an explosion? And the reason they can do this is they have an arc squelching powder inside. You think of a normal fuse, whether it's one of these little things or even a larger, you get a when the fuse blows, you get a little separation. Okay, that separation may be 1/8 of an inch. Well, I don't know if you've ever done any welding, but if you've got something capable of delivering hundreds of amps and you've got an 1/8 inch gap, that produces a really nice arc, and that's how you weld stuff. So you don't want that to happen. Those arcs, with AC, remember that the current is reversing, 60 times a second. So it's not really an issue. But with DC, there's nothing to stop the arc except enough of a gap, enough of an air gap that it can't make it, or something like this arc squelching powder. So, and by the way, when you get these fuses, the ones I use in my system for both for my vehicle and home are nominal 125 amp. Okay, so because that's more than I'm likely to draw at any one time, even with multiple radios going, but enough that if there were a short somewhere, it would take care of it. And these things come in all sorts of ratings, all the way up into the thousands of amps. And each size of these Class T fuses has its own custom holder. So you can't mistakenly, they don't want some maintenance guy saying, oh, the fuse is blown, and putting a 800 amp fuse where there was 125. The 800 amp one has a bigger physical size and spacing. So it's kind of a built-in safety. So that's pretty good design. Now, let's talk about wire size briefly. There are two concerns about wire. One is a safety issue, and that's possible heating. If you use too thin a wire, the resistance in that thing, it's just like in a toaster, is going to end up causing heating and potentially melting the dielectric or starting a fire. Again, ask me how I know. And the other is a performance issue, and that is, you're going to get some voltage drop. Let's talk about that. You know that fatter wire has less loss because there's more cross-sectional area, less resistance. So your voltage is going to be stiffer. And so based on the wire size, based on the load you're going to have, you pick your wire size. And you have to remember that in a DC circuit, you've got the round trip voltage drop. In other words, if you got a 10-foot lead, that's 20 feet of wire through which some resistance is going to drop some voltage. A quick way to do this without consulting tables is, you know, that 10 gauge wire has 1 ohm resistance per 1,000 feet. That's a benchmark. And then you can adjust everything else based on the number of feet, based on the size. Of course, wire gauges, if you every change three sizes up or 3 sizes down is a double or half of the current carrying capacity and half or double of the resistance. So you can, in your head, come up with any given size of wire, and you'll know about what the resistance is. You figure out that times the length. It's linear with respect to length, and you can come with a really good estimate of that resistance, which is probably going to be in the less than an ohm range. You know, not necessarily something you can easily measure. So here's some typical wire sizes, and if you notice, there are different amp capacities for any given gauge, and I just drew this from a lot of different sources, because if you want to be really conservative, you may use this column. This is probably what most people typically use. If your load is only intermittent, you know, you're going to have it for a few seconds and then it's off for a long time, that's fine. And if you're hooking something up just to test and see if it works, you could do this, but you don't want to do it in a regular installation. So let's look at an example. Let's say you've got 10 feet of zip cord going to from your radio to your power supply. And so that's a 20-foot round trip. Number 14 zip cord has about 2.5 ohms per 1,000 feet. Times 20 feet is 0.05 ohms. Now, transmit, your radio may draw 10 amps. If it does, you're going to have a half-volt drop. If it draws 20 amps, you're going to have a whole volt of drop. And do you have that? You know, can your radio still work fine when that happens? And you're going to lose 5 watts, or in the latter case, 10 watts to heat. And again, that lower voltage could affect your radio's operation, especially if you're on a battery that's you know, kind of getting near the end of its discharge cycle. Now let's replace that number 14 with some number 10. Okay, same 20-foot round trip, but you've only got 1 ohm per 1,000 feet, so that's 0.02 ohms. You're drawing 10, you're going to only have 0.2 of a voltage drop. So, and your power, of course, that is lost to heat is proportionally less as well. So you've reduced your voltage drop by like 60%. Now let's talk about generators for a little bit. You got some options. The gasoline power obviously is the most commonly used. It has the highest power density and the highest generator efficiency. They operate over a very wide range of temperatures. The main thing you have to be concerned about is fuel storage. Is it safe? Is it going stale? Is it going to, you know, crust up inside the carburetor? There are ways to deal with that, but generally speaking, you know, if you have a generator at home, likely this is what it is. Now you have some that are multi-fuel. They can run off gasoline or propane. You may have to make some sort of change in the carburetor. Propane is really, it's easy and it's safe to store. When it's not used, there's no gumming up of the carburetor. It's just gas. But remember, when the propane is in a pressurized container and then it kind of comes out into a, you know, expands out into a tube to go to your load, to the generator. Remember, that's kind of how air conditioning works. And so it's possible for that valve because that's a you know, that basically cools the thing. It could freeze up at lower temperatures. So consider that. And also, basically, propane has a lower power density and efficiency. If you have a generator that's designed to run on gasoline, you modify it for use with propane, you'll get less overall maximum output, and that may not matter. You say, hey, you know, my loads are only 800 watts, and this is a, you know, 1500 watt generator. You don't care about a little difference. The efficiency will be a little lower, just so you're aware. Now, talk about solar generators. Um, uh, the term solar generator is a little misleading, I think, because it doesn't generate anything. It's a combination of solar panels external to the generator, and then basically a deep cycle battery of some sort, and uh, either an inverter so that you can run AC things, or DC voltage converters where you can plug in some you know USB chargers or something like that. Uh, the problem I find with them, and they may be great for certain situations, but generally speaking, lower capacity than you'd have with you got a couple of 100 amp hour batteries that you normally run your equipment off. Most of them don't come that big, although you can add layers to it, maybe, and add additional battery capacity. But uh, and then you have to refuel them, if you will. And depending on um, how many solar panels you have, and usually there's a limit on those things as to how much recharge current they can take at one time, which is a practical limit. There's no point in having more solar panel capacity than this solar generator can accept in charging current. Then it could take you hours. I mean, how long does it take to refill a gas generator? You let it cool down, you refuel it, and you're back in business in 10 minutes or so. Whereas you may have to wait hours for the thing to refuel, if you will. And of course, you're not going to have any refueling at night because there's no sun. If the battery in that solar generator is a lithium ion battery, there are always some battery safety concerns for something that big that is known to be a high flammability and explosive hazard. If there more and more of them are putting, the manufacturers now are putting lithium iron phosphate batteries in. I saw a really interesting video, courtesy of our friends at Bioenno. They pointed me to this thing where it was somebody's fire department did flammability tests of lithium ion batteries and lithium iron phosphate batteries. The lithium ion batteries, once they got to a certain temperature, just went off like fireworks. The lithium iron phosphate batteries burn pretty much, just a slow burn like any other combustible material. Big difference in safety. And as always, when you get a solar generator, you can't really see under the hood. You don't know what quality of components they're using. If you put your own system together, it probably will be more expensive because they have the ability to get efficiency from volume. But what you're putting in there in terms of quality of the various components. Our Los Angeles section manager, Diana Feinberg, AI6DF, has done a couple of really excellent presentations on solar generators. One is on an earlier RATPAC, and then she's done an update since then. So if you can, you may want to check out the one she did on RATPAC, or maybe even contact her to see if you can get the updated version if you're really interested in solar generators. She uses them quite a bit, so and she's done a lot of research, and she's bought different brands and started to really look at the operational effectiveness of each one. If your generator is run outside and goes into a building, theoretically, you're supposed to ground it. Now, here in Southern California, pounding a stake into the dry dirt does almost nothing. It may satisfy a fire code requirement, but it's really not going to help you any. If you've got good conductive soil, maybe a little better. I got this tip from several of my folks in the auxiliary communication service have been in the movie industry, and they have requirements. If they're going to run generator power inside a building, they have to ground it. If it's all outside, they don't. Keep exhaust away from enclosed areas. That should be a given. And that means don't run it outside the window with the window open. Okay. I mean, even that, first time I gave this talk, I just saw it, our news article, family of 3 or 4, in a power outage. They had their generator outside, but it was under a window, and they all found them all dead of carbon monoxide poisoning. So well away of enclosed areas. That's your car, your tent, your house, a garage, whatever it may be. Keep your fuel in proper and safe containers, and keep it preferably in an area that doesn't have a combustible material around it, like dry brush, which is very typical around here when you're out in the mountains. If you don't have a U.S. Forest Service approved spark arrestor, put one on. Most of the good ones these days do. So, but some of the old construction generators may not. Have a fire extinguisher and know how to use it. Okay, you have to have that pull, aim, squeeze, sweep mantra, and be ready to use it at any time. Try not to refuel spills onto a hot engine. This is less of an issue with the enclosed generators like the Honda EU series, for example. But if you've got a construction generator where it's an open frame, it's possible that you could spill some of that gasoline onto the hot heat sinks or something. And remember, it's vapor that burns, and that could be a problem. So allow it to cool off for a little bit before you refill. Let's talk about photovoltaic real quickly. They're renewable and, when in operation, pollution free. They're not pollution free to make them or to dispose of them when they've reached their useful life, but when they're operating, they don't put out anything that's harmful. You'll typically get between 5 and 12 watts per square foot, depending on the quality of the build. The cost anywhere from $1 to $12 a foot or per watt, and it's been dropping again. The solar panel costs are way down from what they were, 5 or 10 years ago. Now, let's assume you're using a nominal 12-volt panel. Remember, those panels aren't all 12 volt. You get, so, hey, I got all these panels that are made for a rooftop. Well, they're nominal 48 volts, and you put that into a charge controller that's designed for a 12-volt system, you're going to burn it out. And even a 12-volt, nominal 12-volt panel, when it's unloaded, the voltage could be well over 20 volts, and you do not want to connect that directly to your equipment. You will blow up your equipment. You also have the issue of reverse current flow at night. If you leave the panel hooked up to the battery at night, believe it or not, some of that current flows back out to the panel. So you can use a charge controller, which is the best solution, a diode, which will have a little bit of drop in it, but it'll prevent the discharge, a switch, to disconnect it. You got all sorts of form factors on panels. The highest cost per unit per watt tend to be the ones that are the most convenient, the foldable, the flexible, and the ones that are lowest are the big panels that may not even fit in the back of your car, but they're designed for rooftop or freestanding installation. About the rating of panels, there's a voltage discharge, voltage versus current curve you see here. When you're not drawing any current, you've got that 21, 22 volts, whatever it is, VOC, voltage for open circuit. Okay. And then as you start drawing, the voltage goes down and settles out at your ISC, which is short circuit current. In other words, you put a short circuit on the output, that's as much current as you can draw. So think of solar panels as a fixed current source, if you will. So what do the advertisers do? Well, they look along this curve and say, where is the product of voltage and current the highest? And that's what they'll put on the advertising. Okay. So just because it says it's a 100-watt panel doesn't mean you'll get 100 watts worth of power out of it. So think about the current you're likely to draw. Again, think of it as a current source, not a power source. What about wind? Wind can be a complement to photovoltaic. Sun goes down, wind starts coming up. There's some really neat wind generator designs. You've probably seen the old 3-bladed ones that are put up in large quantities up on hilltops in windy areas. And that was really big when the tax credits were available, and they were basically tax minimization schemes that happen to generate power. You have to be careful though, because typically the voltage varies with wind speed, and that means compared to a solar panel, you can have big swings in your output voltage, which means a charge controller that's designed for solar may not be adequate for wind. I've got a charge controller that can go from 15 to 70 volts, and it will then put out 12. So that's the sort of thing you might need. And for the ones with the rotating prop type blades, um, I've been around these things from Canada to central California and out in the desert. And there's this low frequency rumble. If you imagine driving your car and you open one window in the back and you hear this, this thump, it's almost subaudible, but you can feel it in your head. That's what some of those things can put out. The the axial types, where it looks like a strand of DNA and it's spinning around on a central axis, those tend not to have that problem. Um, here's voltage output versus wind speed, and you can see that the RPM, as the RPM goes up, it's pretty much linear. Your DC volts are going up and up and up, and here you are 55, 60 volts. So with wind system, you could be looking at up to 60 or 70 volts. There's all sorts of good information. I mentioned, you saw that spreadsheet I was using that had a page for loads, a page for sources, and a page for power. We've actually got that as a download available on the ARRLLAX.org website. And so you can use that or create your own to suit. I used West Marine for marine wiring capacity charts. Those tend to be fairly conservative because if something starts a fire in a house, you can go outside. Something starts a fire on a boat, you don't have a lot of options. So they tend to be fairly conservative. Data on AGM and gel batteries. They got a technical manual at eastpen-deca.com. East Penn makes locomotive batteries, and it's their Deca that I have the gel cell. So they're very well made. But again, subject to the limitations of the chemistry. There's a guy in Canada, buckman.ca, where he has kind of a rechargeable battery handbook. I think it's still up. And then if you want a reminder on how to use Anderson power poles, which has pretty much become the standard. We used to use Molex doghouse connectors and so on, but you need males and females. The nice thing about the power poles is they come in different sizes for different current capacities, and B, you use the same hardware, whether it's the source end or the load end. You just set them up so that you turn them upside down and push them in. So that OC Races is one of many sources you'll see on the proper orientation of the typical 45 amp power pole housing. Those power poles, by the way, they have 3 sizes, but it's the contacts that you change. The contacts have different barrels in the back as to what size of wire you're going to put in. You have a big barrel and you put in a little skinny wire, it won't hold it. They have little skinny barrels for the small wire, bigger ones, and then the biggest ones for the 10 and 12 amp. And the 45 amp power pole is not the only one. You've got much bigger equivalents of the same thing, just on steroids. I use 75 amp power poles, which typically use number 6 wire. And I use that for, let's say, the output of my 100 amp hour battery. If I'm going to distribute that, I got a distribution box. I can make it split out as 3 or 4 45 amp connections. And I also use that as the output of the power cables that I run from my AGM starting lighting battery in my Forerunner. So I keep my own separate lithium iron phosphate batteries when I'm out doing radio stuff. But if necessary, I can plug into that system. And if I'm mobiling with the engines running and everything, that's what it runs it on a day-to-day basis. And so I just have the power poles under the seat, plug in the radio, and we're good to go. So that's pretty much the detail. So let's go ahead and stop the sharing and see what sort of questions we may have. And you can stop highlighting me. They don't want to look at me.
Hold on.
There we go. Okay, questions, suggestions, comments? I could not have answered all your questions in that.
One of the things from chat about the quality of fuses, Chinese fuses versus American fuses.
I'm sorry, I didn't quite get that.
I guess someone did some testing on Chinese fuses versus American fuses, and so
Uh-huh.
the Chinese fuses were totally failed versus the American fuses.
Gee, what a shocker.
I know.
Yeah. Stick with good name brands, whether it's coax or fuses or power poles. I remember we had a installation up at a fire station and the stuff just wasn't working reliably. And the guy the ham who put him in, he was fairly new at the time, and he had bought quote unquote power poles off of eBay. I mean, off of Amazon. And it turns out they were Chinese copies. I looked at them. I could tell right away, just looking at the contact structures, these were not Anderson power poles. They were a knockoff, and they didn't work very well at all. They were very unreliable. The mechanics didn't work well. So we cut everything off and put real ones on, and that took care of the problem. So yeah, stick with good name fuses as well. Thanks for that, Barry, and whoever put that in chat.
Yeah.
Others? Okay, if not, let's call it a night.
Thank you all for coming.
Yes.
Thank you, guys. Yeah, it's good group today.
Good
And
presentation. Well thought out. Well done. Thank you, Marty.
thank you. And if anybody has specific questions, feel free to give me an email and we'll see if we can answer them.
Okie dokie.
All righty. Everybody have a good night. Stay safe.